has been described as convergence and divergence, or degeneracy and determinism. And the measure itself is going to be called effective information. So anyone have questions until this point? Okay. Oh, this is fun. So I was giving this talk at a conference on causality about a year ago, and it was scary because people who do research in causality are generally right, and they're more right than I am usually, and so very timid. The ways to think about causality, to me, I think, are as follows. One of the ways you can sort of get at it is to run an experiment. I like this approach. You can infer it using some sort of information flow measure. You can avoid confrontation and study something else, which is actually my preference. The talk list at this conference that I recently went to was looking at information flow between time series. Okay, so starting off kind of nice. Testing the significance of transfer entropy, which is sort of getting at this information flow. A critique of transfer entropies, and then a critique of transfer entropies. And then I could only assume what the next talk was called. So that the way into this conversation that we're going to get, or the way that we're going to get into this conversation is with this notion of effective information. So it's been around for a while, but it's sort of only recently become relevant again. So it's the information generated when a subset of a system enters a particular state out of its repertoire, but only to the extent that such information can be integrated, i.e. as a result of causal interactions from the system. That is a relatively convoluted definition, but the important part of it comes like 10 years later. So by perturbing a system through its entire repertoire of possible states, and evaluating the resulting effects of those perturbations. So I have some system, I'm going to poke it, I'm going to observe what happens, and I'm going to measure the distance or the divergence between the effects, the distribution of effects following my intervention, and some distribution of possible causes. So I'll get more into that. So in a way, this is a run an experiment kind of measure, although run is going to be in quotations because I just have a network, I don't have anything to experiment on it with. So I'm essentially going to, these are nodes, these are links. You can describe transitions in this network using a transition probability matrix. I'm going to build up this measure kind of slowly. So this is our network, this is what we're representing it with. Each node has some outgoing wave. So C, this says, with 100% certainty, if I were to drop a random walker, say, or if this were a button, I could press it, all of the random walkers, all of the energy go to B with 1.0. Each node has this outgoing vector of weights, so it's dropping of this random walker into the system. Similarly, each node could have been caused by a number of different nodes, so you can look at the sum of the incoming probability weights that are coming into it for each node. And then essentially it can be a normalized vector of in weights. So this is the outgoing transition probabilities and basically the mean of the transitions. So put a different way, it's a histogram, and I'm going to be comparing iteratively each node's contribution to the certainty of next states in the system with some average of the whole system. So this orange one is going to stay constant, and these blue distributions are going to be compared each time. There's a pop quiz. So if I wanted certainty about what's going to happen next, which network do I want? So I'm going to say this is more deterministic, or it has higher determinism. So every state determines the future much less uncertainly. If I wanted to be certain about what caused me, or if I want to be more uncertain about what caused, it's this one. This one has higher degeneracy. So more things could have possibly caused it. So if I look back in the past, I'll be more uncertain. And so I want this measure to kind of capture both of those things, and in fact it does, using this Kullback-Leibler divergence between each of those distributions that I was showing you previously. So essentially what this is the average of all of these little distributional comparisons. And it gives you a number, 1.23 bits. We've done it. What this number means is, I guess, sort of much more up for interpretation, and that's what we're going to get into, but we have a number. Put a number on a network. That's our goal. So it quantifies some sort of causal structure with these hypothetical interventions, tossing random walkers and seeing where they go. It could be a different set of dynamics. All I need is just some way of assigning the probability of a given state following another state. So I'm going to just walk through some, maybe not results, just still more description on these model networks, and then I'm going to get into some data. Okay, so what are these two plots, previewing them? On the horizontal axis is the size of the network. So I'm going to just keep getting larger and larger networks. On the vertical axis is the effective information. And I'm going to basically compare two network models. So on the left is this Erdős-Rényi random network, which is just parameterized by the number of nodes and the probability P that any two nodes share a link. And on the right, I'm going to look at some nonlinear preferential attachment, which essentially is parameterized by alpha, which you can think of if alpha is minus infinity, then you just have a nice chain. So every node is going to have degree 2. If it's positive infinity, it's a big star. And then in between, it gets interesting, and at 1, it's especially interesting. So what happens in Erdős-Rényi networks? Something kind of clear is that after a certain point, after a certain size, given a density of network, the network will not increase at all in its effective information, which in a way is kind of a little bit obvious, because the more and more fixed this density is, the more and more links there are in the network as the network grows, and we don't want links if we want to be certain about what might have caused it.
Does it generate the directions in the Erdős-Rényi?
So these are all undirected. I can do it so that it's
so
randomizing directions or
so you're doing it undirected.
Yeah, but the same thing holds if I just randomize the direction.
Oh, yeah, really?
Yeah.
Okay.
Wow.
That was the notion of cause if it's undirected.
Huh? We can cause each other.
Okay.
With more density, you get less effective information. So this darker blue is lower on the effective information. And after a certain point, it just stops growing in effective information. It's not the case, though, with more heterogeneous networks. So on the color scale, I'm plotting different levels for alpha, which is this exponent that generates like how star-like your network is. So if alpha is very high, you get to be a star-like network relatively quickly, and those tend to have very little effective information. On the other hand, these three at the top, it still increases effective information as the network grows in size. So if you just take a step back and think about any networks that you're dealing with in your own lives, there's bits of this type of structure in many of them. So there's hubs a lot of times. You might see some star-like motifs, or there's dense subgraphs. You might see these communities, and intuitionally you start to realize that these types of structures don't actually contribute a whole lot to the network's effective information. So we'll come back to that a little bit. I'm going to skip this. I'm so sorry. I wanted to show this again.
Good.
Okay, so quickly some real data. I'll do a brief dive into some just data from the internet, and then all data from the internet that I get, and then a more deeper dive into a specific data set. So does anyone know what this website is?
Yes, I know.
Networks from there. It's great. They just have a bunch of networks and a lot of metadata about each of them. You can just download all of them. So I ended up just getting a bunch of them, and hopefully you can't see this because I want to show you a nicer one next. Actually, no. So the networks that I was looking at span brain networks, citation, computer networks, human contact, human social, the power grid, social networks, software, technological networks, etc. And if you kind of group these by 4 basically main categories, like biological, informational, social, or technological, you have your own consolidated plot. And the main takeaways of this are that the red violin is the biological networks. On average, they have less effective information, and they span much wider regions of this plot. And the technological networks, which are, I guess, thought to be more synthetic or human-made, maybe have less noise or less of this redundant, non-effective informative structure. So keep that in the back of your mind. Dive into that. I don't have any allegiance to these networks. I think it's a great tool, this Connect database, but it's just networks that don't really have context in my life. One that might is got much more interested in evolution recently. My roommate for summer school that I was at over the summer was an evolutionary biologist, and so he would like wake me up in the morning with fun facts about proteins. And in particular, this paper was I think, where I kind of got really interested in it for 2 main reasons. One of them is it's a very cool paper. Has anyone heard of it or read it? So it's the evolution of resilience in protein interactomes across the tree of life by Marinka Zietnik and her colleagues. The first reason why I like this paper is because of this. I'm not going to read it to you, but the main points are they have protein interaction data, they have lots of it. It's so well formatted too. It's just like 1800 .txt edge lists where the names of the proteins correspond to metadata about them in a separate file. They have like, they do it all for you. It's really nice. And there's also information about where each protein interaction network is in the tree of life. So you could, if you want, you could make your own tree of life out of it. And essentially this is what they find. So on the horizontal axis, it's not time per se, but it can be thought of as similar to time. So if you think of evolutionary history progressing, there's some measure that they're interested in. It's called this network resilience measure. And on average, it's going up. So looking good for the eukaryotes later in evolutionary history. So I thought this result was nice. I went to their website, downloaded their data. Don't worry about this weird curve. I'm bad at curve fitting, but the result is
so that's the actual.
Yeah. Because it's so easy to just get the data. This might be a horrible plot, and so I apologize if it doesn't actually replicate it, but the result is there. So all this is to say, I got the data, and I was trying to figure out some way of, like, oh, I have my own, I didn't make this. I have my own like measure of choice. I want to use this effective information. I have a hammer, found a bunch of nails. I'm going to try it. So what I'm going to do is I'm going to make the same plot with the evolution nucleotide substitution per site on the horizontal. And instead of resilience on the vertical, I'm going to do effectiveness. And so my prediction is like, pew, and then I'm going to just separate it by the archaea and the bacteria and the eukaryotes. And these are all the prokaryotes and those are the eukaryotes. And this is what it looks like. Paste. But this, I think, is quite important for the next part of the talk, and in a sense motivates a lot of the reasons why, like, this idea of effective information is arbitrary. It's just some information theoretic tool to put on a network that can give me a number that can describe the network. What it actually comes into, what I find to be interesting and useful about it, beyond just being a fun network measure, is this plot. So we're gonna unpack it. But I was pissed.
I mean, it sounds to me like this kind of measure would be valid for pathways that are actually turned on in cell types. Like no cell contains its own, it's the whole interaction, it's always subgraphs. right? And that's
At any given
that-
time, it's
at
all.
any
Yeah,
given
yeah.
time in a cell type, it's a subgraph, and like that you can get through pathways, and I feel like that would be the unit of investigation for an information theoretical measure like this type.
I agree. I will also say that the motivation behind making this plot was very. I was a much younger person 1 month ago.
But also, I have a question about your nucleotide substitution per site. Is it what type of loci is it looking? Because you have like,
Let's take that after.
Okay.
I will ask.
Evolutionist
Maria,
speaking.
Can I just ask, maybe I didn't get what effectiveness is, but isn't it related
Oh, yeah,
to
sorry.
entropy?
Yeah, I'm sorry, I didn't find. So effectiveness is just a normalized version of effective information that's bound between 0 and 1.
Yeah, I mean, but if I got it right, effective information is related to the number of possible states that
Mhm.
give me a macro, but that's entropy kind of,
Yeah,
isn't it?
another way to put it is just the entropy of the average entropy of the outweights in the network minus the entropy of the average outweights.
Mm.
So that
Okay.
basically I can,
Yeah, it's another formulation for
yeah.
this. Okay.
Yeah, there's a bunch of ways to arrive at this this type of measure. But okay, so making this plot in general was ill-advised because I didn't know what I was talking about. Still probably don't. But the bacteria and the archaea, or the sort of prokaryotes in general, didn't have this low effective information that I wanted. And so this leaves us at the actual fun part of the talk. How much time do I have left?
Oh, how much time do you need?
It's an hour and a half. So who knows who this is? This is Borges. Who knows this short story? It's called Unexactitude in Science. This is the entire short story. It's about these cartographers who set out to map the territory that they live in, and so they're maybe too good at their job because the map just keeps getting bigger and bigger, and suddenly the map is the size of the territory that it's supposed to be a map of, and Borges notes that that vast map was useless. This, but for network science. So I had seen this paper on the internet a couple of years ago. It's by the co-author on this work. It's called "When the Map is Better Than the Territory," and that's first when I got introduced to this idea that causal emergence could be this thing that could help network science out a little bit. So what it is a phenomenon where a coarse-grained macro-scale description of your original network has more effective information than the original microscale. So what I was looking at with the protein networks was this micro-scale description of this network. What if I kind of chunked them together in some way, said these nodes aren't really giving me anything, I'm going to group them together and make that macro node. And I iteratively find these macro nodes in this network, I calculate the effective information of this, and I compare it to the microscale. If it has more, maybe I like that one more. I'm going to skip this. You group, there's a process to it. So if you remember the preferential attachment networks from before, where this alpha term basically tunes how either snake-like or how star-like the network is, we can look at how a causal emergence algorithm would want to group certain nodes in this network together. So I've colored the nodes based on what's going to eventually be grouped, and as this alpha parameter varies from, say, -5 to +5, what it wants to do is it wants to group states of high uncertainty, states that don't contribute a lot to the effective information. And so you'll get these weird sort of coarse grainings, but that those coarse grainings will have higher effective information than the original network. So two things that I'm interested in here. The causal emergence as a quantity is the difference in effective information between the microscale and the macro scale. So if the macro has more, this will be higher. As a function of alpha, this parameter that makes it more or less star-like. And then I'm also interested in the size ratio of the microscale to the macro scale. So in the far right, there was the star. It just got grouped together into 2 nodes. That's a huge reduction. That's a huge network compression. And so as this alpha parameter increases, And also at 1, there's fun stuff that happens. There start to be sort of regimes of interesting higher order structuredness that show themselves, which is that in the lower values of alpha, you don't see a whole lot of higher order structure start to show itself. But then suddenly, once you get past 1, there's this whole regime of networks that sort of want to be coarse-grained. Similarly, the size, the ratio between the macro-scale network to the micro-scale network drops off massively.
What do you mean by they want to be coarse-grained?
This is me anthropomorphizing everything. They want to, in that it's much more easy to detect, or what they have is motifs that don't contribute a lot to the effective information. And so what that suggests is that there might be a way to reorganize those motifs or group them in some way that increase the effective information. So they want to, insofar as their structure permits that. In Erdős-Renyi random networks, I don't know if you can see this in the back, this is just a tiny value, this is 0.05. There's basically no causal emergence in DR networks. And if there is, it's only in sparse networks. This is a plot. This is basically a stochastic block model of that's looking at 2 different groups. So if you have 50 nodes on this side, 50 nodes on this side, and each group only communicates with themselves, you are down here. So more clique-like and more symmetric in terms of sizes. If you have fully the opposite, so 50 nodes over here, 50 nodes over here, and they only cross-communicate, down here. If you have size asymmetry between the groups, these parts, up here. And there's regimes in this space which are more amenable to causal emergence and more that show higher causal emergence. I'm not going to go into that more. People have used this to study hearts recently. So, does anyone know what atrial fibrillation is? It's a sort of irregular. You can see the signature of atrial fibrillation in these types of time series of the heart. And what they found is that if you group in a way that maximizes the effective information, you start to see it be associated with onset of atrial fibrillation. People are using it to study consciousness. We're going to go back to this plot, and I'm going to re-plot it in the ways that we were typically plotting the causal emergence stuff, which is size ratio, macro scale to micro scale, the amount of causal emergence, and then a summary. So what we started to see is that the size ratio in the eukaryotes, they experience much more network compression. They experience much more causal emergence. And if you group them basically together, you start to see that there seems to be a difference in the higher order informational structure, in the protein interaction networks of prokaryotes and eukaryotes. And we just, this thing I talked about network mergers earlier, we just submitted a grant that basically was like, is there a way that network merger theory can explain this?
No, but you know, because there's a thing between prokaryota and eukaryota that suddenly you have like unlimited energy in eukaryota because you think that you, what do you call, you have the, what is called in eukaryotes? Mitochondria, thank you. You have a patient, so you actually can allow yourself to have an uncompressed biological networks, right? Whereas in bacteria and prokaryotes, you have no energy to replicate anything. I mean, you have very limited resources, right? So you need to compress everything to the bare minimum.
Yeah,
so
yeah.
It's very, it makes a lot
And
of
so,
sense.
you have this sparse, effective sort of causal structure. I mean,
Yeah.
not causal, but I'm going to race through a description about this fun collaborathon that we did, but with the expectation that I'm going to be here tomorrow, and I would like
Yes.
love
If you
talking
need
about
to,
this
if
stuff.
you want to discuss with Brennan, you can shoot an email.
Okay, so background knowledge. Do people know what reconstructing networks from time series data is or not? Because I think that's actually quite a fun part. So it was a group effort. I had a bit about is, but I'm just going to scroll through these slides. This is a little bit of the unwind about how the collaborathon happened. It's this many people contributing. There's a bunch of PhD students, 2 of them are on the job market, a bunch of faculty, and in Sam Scarpino's course, who's a network biologist, sort of ran against this problem, which is that if you have a bunch of neurons, and right, like we're good network scientists, so what we're going to do is just draw some nodes and then connect them with some links, and that's that. Right, seems easy. And this is actually quite a general problem in complex systems research, where some system produces some interesting behavior. We put sensors in that system to collect data about how that behavior is operating. And then we use the time series of those data to actually understand the system. So this could be the brain, we do some neuroimaging, and we make some theory about the brain. This could be Twitter, and we do web scraping, and we make a theory about Twitter. This could be a genome, and we do genome stuff to it, and then we make some money. So the general structure of this problem looks like this, where there's quote unquote some true network structure, or at least we're assuming that there is one, that we have access to with our recording that we can reconstruct. And a lot of the research around this topic has been how can we most accurately do this? And there's a lot of people who have a lot of different ways of saying this is how you most accurately do it. There's way more than 39. I just put 39 as we ran out of space. I'm not necessarily interested in the best reconstruction techniques, and I, in fact, think that one doesn't exist. However, I do think they are similar, or there are similarities between the techniques that are more suited to certain dynamics and certain network structures that might correspond to the types of networks that we see in different systems. So there might be really good brain network techniques, there might be really good ecological network techniques. So this is sort of the goal of the whole pipeline, is to have some true network structure upon which we simulate a bunch of dynamics, which we then use to reconstruct a network. And what we're going to do to compare the network both to the ground truth network and to other reconstructions is we're going to measure the distance, this graph distance between the networks. So the rest of this talk is going to speed through this fun Python package that we made. It's called NetRD. These people all made it. There's an online explorer where you can explore around with it. Yes?
So what's the relationship between the complexity of your network and the resolution of your time series that you need to make such thing work properly?
Yeah, so that was one of the motivating questions, and I still don't have an answer because so much of it depends on the actual dynamical process that you're putting onto the network. So it's this multi-axis thing where the network structure is one component, the particular dynamics, and then the particular reconstruction that you're using, all of them being compared to the original network structure. And a lot of it's just an enumeration thing where you just need to run the experiments. And,
sure, but with the signal that you have and that you use to rebuild your network, you could actually subsample it and see what's the minimum subsampling you need to actually get to the correct network configuration, right?
That's
so
right. That still does depend quite heavily on the dynamic. So if it's this like spiking neuron model or some like icing model dynamics, those will be differently amenable to reconstruction and to subsampling and to like injections of noise. So we try to adversarially get around it. I don't have like a one answer for that, but the goal is essentially have like an index where you can pose that question, or where that question will have been posed, and in some supplemental material it'll be there. So just check today at 4 o'clock. There are 5,000 people who have downloaded this package, which is terrifying. It's called NetRD, and so it does 2 main things, maybe 3. The first thing, so the 0th thing actually, is that it simulates dynamics on networks. So I say, I want a time series, I want to simulate a time series. I have a network, give me some n by l time series object that I can play with. So that was what we saw in the previous plot. Or if you like brains, things like this. The second part is the reconstruction. So we have a bunch of techniques for, given a ground truth network, given a time series that's been sort of simulated from that network, what do the methods do? And this is some sample of the methods that are in the package. This is a particularly unfair example because this is an easy network to reconstruct using easy dynamics on it. Real networks and real dynamics are never like this, and so there's a relative correspondence between the methods, but don't expect that ever. There's different ways of thresholding the subsequent network, so a lot of it gives you like a weighted adjacency matrix that looks like this. This is a clique if you just say give me a network, or a fully connected network, and so we can cut off a bunch of the erroneous edges. My favorite part of it is the graph distance part. Graph distance, I'm going to quickly explain using this example. So how similar are these two graphs? 4. How similar are these two mugs? And it, of course, depends on how you measure similarity or distance. So you can say how do their positions differ. You can say that in meters. You can say how much volume they differ in, how much temperature. And so there's essentially this structure for graph distances. There's a lot of ways to compare graphs, and we basically implemented all of them into this package. We invented a couple new ones at the time. I don't want to keep too much. I have a whole thing about graph distances, but I will scream about that later.
We're only 299 slides, so.
Oh, there's 320.
I really?
200 total?
20. So just in general about this, I thought that this way of doing science was actually quite a productive one. Counterpoint, the paper's not done yet, so maybe it's.
Right, actually, such a paper.
You keep rewriting it because everyone has thoughts. There's a lot of people on the paper, they all have thoughts about the paper. It essentially was this, but for the last 6 months. I was going to get to some theory stuff, but mostly this is good drink conversation. Okay, oopsies. So, okay.
Thanks a lot.
For those of you who need the reference in the title, I make art sometimes that just is typing words. So this was the reference. But thank you so much for letting me go over, and it's been a blast being here.
It's very late, but maybe if there is like a question or two, like yes.
So when you are looking at your network and you want to group certain nodes so that you can essentially reduce the complexity of the network, how can you be confident that the nodes that you are grouping actually don't give some interesting properties to the overall network? So
I'm not. Okay. Like